Welcome back. So it's me again. And I'll talk about, okay, let's see. So this morning's lecture, I'm afraid parts of it might be quite boring, but it's meant to set up the important concepts for what will appear later today. So call it fractal uncertainty principle. Simple semiclassical analysis. And if we suddenly still have time, which is highly unlikely, I'll talk about hyperbolic dynamics a little bit. But probably we'll just stick to the first two. So I should say that today we have 3 talks in the workshop. And the 3 talks present essentially this control of eigenfunctions theorem that I stated in my talk yesterday. It's just split into 3 parts because it has different components. So I got maybe the more boring but important, I guess, elementary setting up component, where I will introduce fractal uncertainty principle, some related concepts, and it will be in preparation for other lectures. So what's the plan for today? Reixiang Zhang will give a proof of fractal uncertainty principle, which will be almost entirely classical harmonic analysis. That will be the flavor. And then Longjin will show that fractal uncertainty principle gives this control of eigenfunctions, which was advertised yesterday. And that will have some dynamics and a lot of microlocal analysis. And so my talk is meant here to somehow provide both background for Zhang's talk, because the proof is kind of technical, not technical, but it is a complicated proof. And so to provide some more light-hearted background, and also to relate this fractal uncertainty principle to semiclassical quantization, which will be used in Jin's talk. So in this sense, I think this talk is important, even though, again, some of you, depending on your background, might be somewhat bored. So the first part is I'm going to talk about fractal sets. So I need to people have different understanding. Did I press the button, by the way? It's recording, right? OK. Fractal sets. So we need to have a formal definition of what a fractal set is if we're going to stick it into an uncertainty principle. And in fact, there are 2 definitions. I'll give both of them because both of them are important in different applications of that technology. And I'll explain also how they are equivalent in a certain sense. So the 2 definitions, one, it will be what I call delta regular, or something you call Alfors-David regular. And the other definition will be new porous. So let me just write them out and then draw some pictures. And we'll develop some intuition about what fractal sets we're actually dealing with. Everything will be on the real line here. So it's all really 1D fractal geometry, which is not the hardest fractal geometry. So these are rather basic definitions, but let me do it. So let's say delta is between 0 and 1. That's going to be the dimension of my set. And I will also, it's convenient for me to fix these 2 numbers, which this will be the low scale and this will be the high scale. So my fractality will happen between these 2 scales. So I'm going to say that set X is delta regular, or Alfors-David regular, of dimension delta, on scales alpha 0 to alpha 1 with some regularity constants. It really should have been there, with regularity constant CR, some number 1, if so if what happens? Well, there exists a finite measure mu such that this measure is supported on the set, this condition 1. So this is a way to measure how much of a set we have of a subset, measure the subsets of the set. Then for any interval, well, I of size between these two numbers, this mu of I is bounded above by CR times the size of I, so the length of I to the power delta. That's where delta comes up, as well as CR. And then if additionally, so if I is an interval that satisfies this property, and additionally I is centered on X, so the center of I lies in X, then you have a lower bound. So that's the definition. So what this definition means is that you... Yes, so there's probably lots of names. So when I learned that the person who taught me this condition called it Alfors-David regular, but I'm not sure this is maybe even the best pair of names to attach to it. But right, so it's a very classical definition. This is really basic fractal geometry. This is not a, it's not nothing microlocal or harmonic analysis about that definition. So what it tells you is that if you have, so in practice what will happen is my scale, usually it will be between 0 and 1, or it will be from h to 1, where h is this effective wavelength, which is extremely small, and this constant shouldn't depend on h. So you really think that you take any interval, and then the measure of this interval is proportional to the size of the interval to the power delta. And so that's a, that actually, if this was true on scales from 0 to 1, that implies that the Hausdorff dimension of your set is equal to delta. But then it tells you much more than the Hausdorff dimension. The Hausdorff dimension always exists. But this regularity property is very easy to not be satisfied because you need the same dimension at all points, at all scales. So here are some examples. For example, this, just one point is 0 regular on scales 0 to infinity. The unit interval is 1 regular on scales, say, 0 to 1, with some constant that can be figured out. Here's an example of a set that's not delta regular, because at one point it has dimension 0 and the other point has dimension 1. And what's a non-trivial example? Well, a non-trivial example is if you, let's say, take mid-third Cantor set, just the usual Cantor set. This is log 2 over log 3 regular. Again, with some constant, on scale 0 to 1, with some constant, for example, 100, I think, would suffice. OK. So that's the definition. So again, kind of, might look kind of dry and boring, but it's, if we're about to speak about higher matters, it's nice to actually know what we are, what definition we're dealing with. OK. So that's the definition of delta regularity. And so that's what I will understand as a fractal set. OK. Now, as I said, there is another definition, which is also sometimes convenient. It really depends on which application you are doing. So for today, actually, this other definition will be more useful. And it's a more robust definition because, as that example there shows, delta regularity is not closed undertaking subsets. So if you take a subset of a delta regular set, you might end up with something which, say, is too small or has too small dimension at some points, and that will not be delta regular. So this thing, definition 2, this new porosity, is actually closed undertaking subsets. A subset of a porous set is still a porous set, which will follow immediately from the definition. So let nu bigger than 0. And again, I have this alpha 0, alpha 1. Then I say X, subset of R, is nu porous on scales, on these scales, if what happens, so this is a shorter definition, for each interval I, so that's the definition I gave yesterday of size between this, there exists interval j inside of I, where the size of j is nu times the size of I, and j doesn't intersect your set.
Here's your big test. We have a physicist.
Oh, God. Well, that's scary. Well, yeah, today is rather technical, I'm afraid. So that's the definition of porosity. So regularity, if you think of regularity directly, it's about counting. It's about counting how much of your set is in a given piece. In fact, this regularity implies a lot of things. As I said, it implies the Hausdorff dimension is delta, the Minkowski dimension is delta. If you fatten, right, if whichever counting, whichever dimension you think about, it's going to be equal to delta. So there's not very difficult ways of showing that. Now, this porosity, you can say, is about having holes in your set. So I have my set somewhere here, and I want to say that on each intermediate scale, so again, this range of scales can be rather large, I can always find a subset which doesn't have, which doesn't intersect. I can always find a hole. I can always find some subinterval that misses my set. Now, it turns out that for some purposes, these two definitions are basically equivalent. So for yes, on the length of it, that's it.
But what does it have to do with set x?
No, it's any interval. So for each interval of that size, this has to be true. Of course, j does depend on I. Right, so for...
Thinking the definition, he's asking where's x?
Oh, here. That's where x is. It's like if you think about the mid-third Cantor set, maybe I should draw this mid-third Cantor set like that. You know what we do in calculus, this kind of thing, or real analysis, I suppose. And then you see that what regularity tells me is that if I take one of these intervals and they count how much of a Cantor measure is in this set, I have a bound which is like the size of the interval to the power delta, right? That's what Cantor measure, that's its property. When I think about porosity, is that if I take an interval of some size, well, I might as well take an interval of size 3 to the minus k for some k, right? I can always shrink it a bit. And then I will always be able, inside of this interval, let's say if this was this interval, I can always find this hole. So if this is I, this would be j. So the set has a lot of holes. Now, it turns out these two definitions are actually somewhat equivalent. I will just do proofs by pictures, because they're really not hard proofs, but it's nice to... yeah, I think that one would be, you can, legally speaking, maybe it's something like 1/9 or 1/10, because your interval doesn't have to be size exactly 3 to the minus k. Certainly, nu 1/100 would work, and the precise value of nu, one would have to think a little bit. But it's, yeah, it cannot be smaller than 1/3, certainly, bigger than 1/3. So here's two statements. But in practice, especially what will happen for today is we will consider delta regular sets where delta is allowed to be very close to 1, or nu porous sets where nu is allowed to be very close to 0. So we'll just care that it's nu porous with some positive nu, or delta regular with some delta less than 1, and we're not going to care too much what the precise value of these are. So here's two statements. So one is if x is delta regular and delta is less than 1, then x is nu porous. Porous with some nu, depending on delta, bigger than 0. So how do you prove something like that? Well, so here's a proof by picture. Take an interval I. Here's my interval I of a reasonable size. And in some of these statements, I might have to change the upper-lower scales a little bit, but I'll spare you that. That's really a technical detail. And you want to find a subinterval j that misses your set. And you have the regularity property. Well, I take some n, which depends on this delta and the regularity constant, which will be a large integer. And then I just divide my interval into these intervals I1, I2, In. So I'll just show that one of these intervals misses my set. So I'll claim there exists j such that ij doesn't intersect my set x. Well, how would you prove that? That's just by counting. So I'm going to cheat again to just not bore everybody completely. I'm going to assume that if not, then there exists some xj in ij intersected x for each j. And I'm going to make it simpler, I'm going to assume that each xj is exactly the center of this interval, which is not quite true. And then you see that if you look at the measure of mu of I is going to be sum of measures of ij. And now you see that this thing has an upper bound, which is CR I to the delta. And each of these things has a lower bound. So the lower bound on the sum would be what? The total number, which is n. And then what's the lower bound on each? It's CR inverse I. Well, what's the size of each of these? Is I over n to the power delta. And then you can see that this is a contradiction if n is sufficiently large and delta is less than 1. You can just see that as n goes to infinity, let's say, this I to the delta falls out, and then eventually this number will become rather large because delta is less than 1. So as you see, it's a very simple argument. It's just the counting. So counting converts to having holes. Well, at each point of x. So here I cheated. I just assumed that my intersection, that the center of each interval. Otherwise, you have to make your intervals a bit fatter. You have something with bounded overlaps. So the same argument works. It just has to be slightly adapted. Right. So you will have, if the points is not at the interval, then you still look at intervals centered at each of these points. And then they would all lie in a slightly fatter version of I, and they would overlap. At most, 3 of these intervals can overlap at once. So you would have 3 somewhere here, I suppose, in the bound, and then the size will be a bit bigger. But it ends up the same.
But mu depends also on this constant CR, right?
That's right. Oh, sorry. Oh, that's so bad. Yes, that's right. It depends on the regularity constant. So the other direction, well, as I said, new porous sets, they don't have to be delta regular. But here is another fact that they can be embedded in delta regular sets. So if x is new porous with some nu bigger than 0, then there exists some x tilde such that it contains x, and x tilde is delta regular, where delta depends only on nu, and it's strictly less than 1. So how to convert pores to counting? Well, that's actually an even simpler argument. Here I really don't have to cheat at all. I'll just take again some n, or let me call it m, which is the CL of 2 over nu. So that's a natural number. And then I'm going to assume for simplicity that my set x is in, say, 0, 1. Why not? And then if I look at the interval 0, 1, I divide it into intervals of size 1 over m. Like that. And then it's easy to see from the porosity condition that if I call this I1 Im, that at least one of these doesn't intersect the set. So you can see from porosity that at least one of these whole intervals should just not intersect the set at all. You had some subinterval of twice as large size, which doesn't intersect the set, so it contains one of those. So let's keep all of these except one, which doesn't intersect the set. There could be more, but let's just throw out exactly one interval. And then let's repeat the process. So each of these things, I divide in intervals of size 1 over n squared. I repeat the process. Each of them, again, is going to miss. At least one of them is going to miss my set. And then I repeat the process as much, until I hit my lowest scale or whatever. And then I get this as my set x. So it's a set obtained by removing these smaller and smaller intervals. And then it's easy to see that x, it looks like a Cantor set. It looks, it's a Cantor set. It's a Cantor type set.
Won't you have a problem with this lower bound alpha 0 once you have the intervals getting smaller and smaller?
Well, so eventually you have to go down. So the scale would be the same for the regularity and the porosity constant. So eventually, if your lower bound, if your lower scale was not 0, if it was something positive, you just stop at this point. And then you got what looks like a union of intervals, but it's going to be delta regular up until that scale too, give or take. And that's going to be delta regular with delta, which is just log m minus 1 over log m. Yeah, so these are kind of simple observations, but I think it's nice to know that these two, because the way both of these definitions are used in the proof. And both of them are used in applications. So for today's application, we are going to use that our sets are porous. Tomorrow, we might use the fact that our sets are regular. All right, so any questions to that, these mostly technical points?
Yeah, the fact that the interval which you remove is not in the same position which has.
It doesn't matter for regularity. So it doesn't have to be, it's not a very difficult argument to check that it's, because when you're talking about discounting by sparing a constant, you can just assume that your interval was one of these, specific intervals of size n to the minus k, which is aligned with the correct integers. And for that one, you have exact counting. And then, you can always embed things into things, and that's all right.
I mean, here, the definition, there exists a measure, so this does not seem to be very easy to check in the norm.
That there exists a measure? Well, here I specify a measure. It's there's an H.L. Cantor measure there.
Somehow is this measure in some sense constructible in general, or can you?
So the measure is extraneous in the argument. So if you want to think of it from a point of view of just fractal geometry, you can get rid of the measure. It's really a question of the following. So this regularity question is really, if I had some interval I, and then I took some constant, gamma, which is less than 1, and I just look at, cover x intersect I with balls of size gamma times I, like that. So like the so-called metric entropy. So that has nothing to do with measure. Then the number of balls, it's like gamma to the power minus delta. That's the same statement. Well, with a lower bound, if your set had a reasonable overlap, like for example, if the center was at x. So it's really that there is lots of reformulations which are basically all the same. And if this is true all the way down to scale 0, then you can just replace mu with a delta Hausdorff measure. So it's really a very, very nice object. But in our applications, well, for that set, the measure is constructed explicitly. For limit sets of convex compact groups, there is natural Patterson-Sullivan measure that satisfies that property. So we can afford to have a measure here. But yeah, you're right. It's really a statement about subsets of arbitrary metric spaces. I guess that's if you want to view it in this highest generality. All right. So now let me talk a bit more about. Now let me introduce the fractal uncertainty principle. Okay, so we've done fractal sets. So now let me introduce this fractal uncertainty principle and just give a few, again, trivial remarks. So the talk by Zhang will really be the first thing where something non-trivial or complicated appears. But it's nice to do trivial things first, to get them out of the way. So what I'm going to do is, I'm going to use this small h, which will go to 0, like what happened in the last lecture. But this lecture will really be not about quantum chaos. It's just as a standalone statement in harmonic analysis, if you want. That's how we'll treat it in the morning. And then Longjin in the afternoon will relate it back to quantum chaos. So this is, you can think of it as a wavelength of the functions that we're interested, or you can think of H inverse as frequency. If you're a classical harmonic analyst, think that you're going to frequencies up to H inverse. Now, I'm going to use the semiclassical Fourier transform, which is just this. So this is a unitary operator. So it's the usual Fourier transform, except it's rescaled. Here, f is an L2 of R. So this is really all on the real line. So the semiclassical Fourier transform, it's like usual Fourier transform, but you can see that the frequency is rescaled by a factor of h. So that's why h inverse is like the frequency at which we're studying things. Right, so for example, if our function f was oscillating at frequency around h inverse, the semiclassical Fourier transform would live in an interval of bounded size. Okay, so that's the scaling. Now, the question that I want to ask is the following. Assume that I have two sets. Again, let me just make them inside 0, 1. And I'll assume that the sets are delta regular. on scales h to 1 with some constant, regularity constant CR, which shouldn't depend on h. So a quick remark. When I think of sets that are regular on this scale h to 1, you can think of it as a union of h-sized intervals, or embedded in a union of h-sized intervals, which are arranged in a fractal way. Also, if you took, say, a Cantor set, for instance, or if you took a set that's regular on scale all the way down to 0, and you took its h neighborhood, so points that are distance h from something in the set, this would satisfy this property. So it's really, you know, I really think of this as just an h neighborhood of a true fractal set of dimension delta. Okay, so again, perhaps a technical remark. But the question is, so can we prove, can we show for some interesting value of beta? So for now, I'll say beta non-negative, but really we'll need to make it more interesting. The following bound that, let me just write it. All arch of h to the beta as h goes to 0. So the situation is the following. You have this small parameter h, it will go to 0. You have these two sets, they are allowed to depend on h. So maybe they're just h neighborhoods of a given fractal set, or maybe they're just some families of fractal sets, but this regularity constant has to stay bounded. That's really what matters. And then what I want to do is I want to study the following operator. Take the semiclassical Fourier transform, which is a unitary operator, and I wedge in multiplications by indicator functions of x and y. And they study the operator norm of that guy.
So beta would depend on delta.
Right. So beta, you know, it should, well, the answer, well, maybe it's true for any beta. Well, that we'll see is not true. But, you know, in reality, yes, it will depend on delta and quite often on the regularity constant as well. So we'll get in a moment to what kind of betas we can get easily. But that's the general question. And there are lots of ways to reformulate that question. But for instance, you can think of it if you're a classical harmonic analyst, and that's what the approach that Reixiang Zhang will take in the next talk. It's really a question that if the support of some function f, if the Fourier support of f is contained in h inverse times y, so in this dilated set y, then the L2 norm of LF on the set X is much smaller than the total L2 norm. That's the same statement. Right, so it's like beta? Yes, so we'll yes, so that's going to be the next board. But that's just, you know, I'm just reformulating the statement because the different people think about these things in different ways. So that's a harmonic analysis, I guess, way to think about it.
Maybe you should say for some positive beta.
Right. So beta equals 0 is boring, but so let's see. Oba. Let me just, sorry, up. Let me just erase this, and then actually I can do it here. So this is kind of, let me do easy things on that board. So what can we do? So beta equals 0 is trivial, right? Just from there. So that's certainly not interesting. There is another thing, which is the volume bound. So I claim that you can get beta equals 1/2 minus delta for free. This uses the fact that the volumes of x and y, so as I said, you know, the Hausdorff and Minkowski dimensions are all the same. So in fact, it's not too hard to show that these volumes are going to be like h to the 1 minus delta. And then there are two ways of proving this bound. But for example, you know, if you're an LP person, exercise, stick L2 to L1 to L infinity to L2, use holder on these two sides, use the standard bound here, or you can bound it by the Hilbert-Schmidt norm, which is equally as good. Of course, the Hilbert-Schmidt norm is explicit. You have an explicit integral kernel, and so that's going to be like the square root of the volume of x, volume of y, divided by h. The division by h comes from that h to the minus 1/2 in the Fourier transform, and so that's really like h to the 1/2 minus delta. All right. So that's what we can get for free. So it's nice to know, sorry, I'll be back up. It's nice to know what we're starting from. So what we get,
Your main aim is just to improve that now.
that's right. That's what we will be doing, yes.
Excellent.
Yes, so if I draw this graph, if I can draw a straight, okay, I managed to draw a straight line this time. This is what we got for free. And I should say that only volume, so if only using the volumes of x and y cannot beat this bound, cannot beat beta equals this maximum of 0 and half minus delta, which I will call the standard fractal uncertainty exponent, the trivial one.
There's no structure on x and y.
Right. So if you're only using the volume, because if you look at x and y, so I call this the brick. If you replace x and y by intervals of the same volume, then you can easily check that this norm behaves according to this exponent. And you cannot get anything better. For instance, if delta is exactly equal to 1/2, then a half-dimensional set up to scale h has volume no more than h1/2. But there is, if you look at just an interval of size h1/2, the Gaussian lives on this interval in both position and frequency. So if you just take this interval of size h1/2, you plug in a Gaussian, you see that your norm, well, it's strictly less than 1, but it certainly doesn't decay as h goes to 0. So
if delta is greater than 1/2, you will not get an non-trivial bound.
at all, yeah, that's right. If you're using
What
volume,
is the intuition behind that?
you will not.
Right, but why is the sets of dimension greater than 1/2 more difficult?
There's nothing symmetric here about x and y. You could just think you could maybe take x bigger and y smaller. Then basically you're recovering the fact that the delta.
Right. So if x and y were equal to each other, then dimension 1/2 becomes a critical dimension. So at this dimension, if you only use the volume, then you could embed a Gaussian into an interval of that size. And so you need structure. And similarly, you won't be able to improve over the volume bound if the sets are thin. So you need structure. Need structure. And that structure is provided by this delta regularity. And it's an interesting question how to use that structure. So John will explain that in the next lecture, how this is actually used. All right. So, all right. Anything else I wanted to say? Probably not. And you can also say, by the way, that in this statement, you really want to go down all the way to scale h. So for some people, it would be more natural to think about h1/2 neighborhoods of sets, because, well, there are reasons for that. But then the statement can never hold. So as soon as both of your sets contain an h1/2 sized interval, this is all lost. So your sets have to be thin. All right. So now let me state a theorem. So if we go look at that graph on the left, so we see the trivial bound. And if we try to improve that, well, if delta is equal to 0, then your sets are like 1 point, and then it's easy to see cannot be improved. If your delta is equal to 1, then you can take your sets just 2 intervals, and then also easy to see that the bound cannot be improved. So the theorem that I will state is that, in fact, I'll state the names in a moment, all other cases improvement exists. So assume delta is strictly between 0 and 1, and x and y are delta regular with some constant CR on scales h to 1. Then we have this bound where beta depends on delta and CR, and it's strictly bigger than, the constant also depends on delta and CR. Maximum of 0, 1/2 minus delta. So you can actually always improve that. And so that will be the topic of this morning, or half of it, half of this improvement. Now you can see that you're improving over 2 different things here. So it's really 2 different theorems. So the improvement over beta equals 0 was done in this paper, joined with Jean Bourgain. So that's beta equals to 0. And then the improvement over the pressure bound was done later in the paper with Jean. And
Meaning delta bigger than a half.
right, so this is only interesting when delta is at least a half. This is only interesting when delta is no more than a half. Yeah. So it only, it's only interesting in half of the cases. The statements are true all the way through. They just become, ridiculously bad after some time. So today we'll concentrate on using this result where delta is very close to 1. And tomorrow we will touch kind of an intermediate range of deltas. Right, and also to be completely honest, this result uses some new technology. This result is it used some technology that I personally learned from paper Frédéric No, and that was based on Dolgopyat's method. So it's a fractal uncertainty rendition of how Dolgopyat's method would work. All right. So, okay. So that's the statement. Okay. So now one thing that I also want to mention, it's maybe something worth discussing in the afternoon for the group, is an open problem. There are lots of open problems here, but the one I want to mention here is higher dimensions. So even let's assume that our sets x and y were just inside, let's say, 0, 1 squared. So they are in R2. You can still define delta regularity in terms of intersections with, let's say, balls, with round balls. You can still define new porosity in terms of each ball. There is a relative.
Do that, maybe you could indicate which problems require higher dimensions.
Right. So if you want to, so this one-dimensional fractal uncertainty principle applies to, for example, proof control for eigenfunctions and spectral gaps for surfaces.
Right, so if you want to go to hyperbolic.
Right. So if you want to, for example, prove a similar results for higher dimensional, so dimensions strictly bigger than 2, hyperbolic, or maybe more general manifolds.
It's going to do with the boundary.
Right. So you reduce the dimension by 1. So if you want to prove something interesting on an n-dimensional manifold with with hyperbolic dynamics, using this technology, you need fractal uncertainty principle of dimension n minus 1. So that's because that really counts the number of stable or number of unstable directions, effectively, this dimension.
Same for if you wanted to prove your topological closure in constant curvature.
In higher dimensions. Right. So this is really, yes, higher dimensions there correspond to things that are dimensions 3 or higher in applications. That's right. So the problem here is that there is a counterexample. And the counterexample is ridiculously easy. I'll just draw it. So this is my x. It's going to be like that. And here's my y. They're just rectangles. If you look at the norm, this is now two-dimensional Fourier transform. Is like 1. But delta here is equal to 1. And so here the whole range of dimensions is between 0 and 2. And so that's something that really, it's easy to check. It's just once these two things are perpendicular, you will have that. If you want a limiting version of that, if you have a distribution which is supported on a horizontal line, you take a Fourier transform with, or just imagine, just take constant function 1 on a horizontal line. You take the Fourier transform with, you will get constant function 1 times delta function on a vertical line. And so all of the mass will lie there. And so in order to understand this higher dimensional question, just having the fractal property is not enough. You need to, I guess, respect the geometry of the set somehow. So that's an open problem. Well, that's so the main tool. So what?
Is there a higher dimensional one?
No. Well, not to my knowledge. So that's anyway. That's something nice to maybe discuss, especially in the afternoon.
So the rest of the picture you're saying goes through this 1/2 to 1/2 to 1. We didn't use anything, so that.
Yeah, the volume bound would be the same in higher dimension. Well, it would be 1 minus delta. So here the trivial bound will look like that. It's 1, 2, 1, like this.
So this counterexample is at the point 1.
Right, it's exactly at this critical point. And for that particular critical point, one can say something. One can try to say the additive energy is better. One can, well, this one is not better, but it's an arithmetic progression. So one can try to say something, but that already would be something complicated that uses something just beyond just counting. So, yeah, if you want to...
What the limit sets look like, about 3 now.
Mostly not, even though for the hyperbolic cylinder, they do look exactly like that. So it's a good question. So it requires some interplay between the geometry of the corresponding fractal set that the problem gives you and harmonic analysis to understand what's even the correct condition to put there. So that's why it's a...
Dimensions, by the way, there are other generalizations of these uncertainty principles using paraboloid spheroidal tape.
So
We use the geometry of spheres.
actually did. So it could be, there could be something, but anyway, so let's this is just to stir some discussion. Maybe not right now, but to stir some discussion during our.
Dynamical level, it feels like it should be transverse to the stable or unstable direction to avoid something like that.
Well, they are already transverse, but you see, you can have two. You can have a stable vector which are orthogonal to an unstable vector. That's the problem here. So what happens, by the way, in the case of hyperbolic cylinder in dimension 3, you get exactly a picture like that, but the lines are never orthogonal. So, but of course, how do you say the two fractal sets are not orthogonal to each other, and what does this even mean? So, yeah. Anyway, so you see there's still stuff to think about. This is certainly
And this
not
also
a...
has a discrete formula. You can formulate the same problem.
Oh yeah, you can,
Dimensions of
and we still don't know what to do with it, right? So it doesn't become easier in the discrete setting. You can reformulate it in terms of the discrete Fourier transform, and that's not going to make it any easier. So now let me continue. And now what I want to do with the rest of my time is I want to explain how this harmonic analysis statement is related to semiclassical analysis. So as much as I can. And so that's whichever statement I will arrive to at the end, Longin will have to use that statement in the afternoon to, so as much as I can do now, he can start from a... Anyway, so if I look at this norm, well, I can for free... So this is, again, we're going back to this lecture. Much of it is kind of very straightforward things. Am I doing it right? Oh, even the trivial stuff I didn't do right. Wow. Well, it is a true statement. But let me stick the Fourier transform here. That doesn't change the norm, OK? And now I'm going to think of it as a product of two operators. So this one is localize in position to y. Right? That's what this operator does. And this is a Fourier multiplier. So I localize in frequency, or in semi-classically rescaled frequency. So you have to divide everything by h to x. So I would like to think of this norm bound, of norm bounds of this operator, as really norm bound on a product of two localizations. And these two localizations are incompatible. So that's what this norm bound, the fact that this is going to be O little of 1, let's say, or O large of h to the beta, where beta is bigger than 0, this tells me that these two localizations are incompatible. If you try to localize simultaneously in position to this set and in frequency to that set, your function, at least a lot of your function has to fall out, at least during one of these two localizations. You cannot have something localized in both. Now, why is this useful? So I think I can erase this now. So I want to relate it to semiclassical quantization. Well, I'm on the real line, so I'm just going to write a formula for semiclassical quantization. So that's this part of microlocal analysis that was advertised. No formula was given, really, by either speaker, because the formula isn't the main point. But now it's a more technical talk. I can give a formula. So here's the formula. If I have a function x and xi, and it should satisfy some reasonable conditions, but I'll ignore that fact, on R2. So x is the position variable, xi is the momentum or frequency variable. I can correspond to it an operator up h of a, which, again, doesn't always, depending on the growth rate, but I'll pretend that this is not an issue. Let's say it's might map L2 to itself, and it's given by this formula. You just take 2 pi h to minus the dimension, which is 1 here, and then integrate over R2 e to the I over h x psi. Well, okay, this is the official standard formula, which and I forgot to stick my symbol a of x psi here. So that's the formula. The integral makes sense if a is compactly supported. If well, you would say, what's the psi integral? Well, if you integrate first in y and f is smooth, then you get something rapidly decaying. Anyway, you can make sense of that integral. So this gives us a way to quantize observables. And you can check that, for example, if a only depends on x, or if a is just 1, for instance, then the corresponding quantization is just identity operator. That's the Fourier inversion formula. And if a has some power of psi, then Fourier transform intertwines multiplication by psi with differentiation. You get a differential operator. If a is just a function of x, then there's no integration in x, so just you get multiplication operator. So you get all these nice properties. Now, I should say that if a is just a function of psi, if you look at this, if you stare at it for a little bit, if a is just a function of the momentum variable, you get a Fourier multiplier. Right? Because you just took the Fourier transform, you integrate out y, then you multiply it by some function of psi, and then you take the inverse Fourier transform. That's a Fourier multiplier. That's a formula for that. So in particular, I can write that my fh star, so this is not smooth, and again, I'll ignore this issue for now. At some point, you might want to take smoothened out indicator functions. But this is really the first operator here is the quantization of the indicator function of x applied to the momentum variable. And this one y is a quantization of the indicator function of y applied to the position variable. So this is really a product of two semiclassical pseudo-differential operators, two quantized observables. And that's how it will be used, because we'll use microlocal analysis to reduce the situation where these two observables appear natural, and then we'll multiply them and we'll take the product. All right. So now one more thing that I have to talk about, because that's a key element of the strategy, is well, how bad of symbols can we quantize? So if we, for example, look at x, so 1x of x. So what does it look like? Well, its support looks like that. It's like a union of these lines, right? With respect to the set x. And the size of each interval in 1y of x, I suppose. The size of each interval here might be as small as h. Right, so I'm thinking of taking h neighborhoods of things, so it can really be tiny, like that. So this function, obviously, well, it might depend on h. And in particular, the derivatives of that. Imagine I smoothened it out a little bit. So I take a smoothened cutoff, but with support in there. The derivatives of that are going to grow as h goes to 0. And eventually, if I try to shrink too much, it will be a problem for my semiclassical quantization. So unfortunately, or fortunately, our argument is taking the classical quantum correspondence to its limit, to the limit of how thinly you can localize, and then you get some improvement. So I have to explain why can you localize to h and not any farther. And that will explain the time of propagation in long stalk and so on. So, well, this quantization has a lot of nice properties. I'm not going to write them all out. But here's a general product formula. So here is a product formula, which is the following. If I try to multiply two observables like that, I will get another quantized observable where this is a reasonable symbol. Well, if these were reasonable, this is not going to be too bad as h goes to 0. And this has an asymptotic expansion. And this expansion, in this case, it's rather simple. So this is an expansion as h goes to 0. It's not a converging series. This is really like a Taylor expansion, if you want to think of it like that. And the way you obtain this is by method of stationary phase, by the way. So that's one of the fundamental technical tools in microlocal analysis. So I'm not going to prove that, but I'll write out this formula. Partial j psi I keep forgetting. I might have screwed up somewhere. I think you need j factorial there. Anyway, that doesn't.
I assume everybody's familiar with Mandus. He was here many years ago, and when propagation of singularities was being developed, they had a special year.
Well, that was a bit of a, I mean, I wasn't even alive.
Doesn't matter. You should
Right. But anyway, that's the formula that you get. For this quantization, in general, these asymptotic formulas can look more complicated, though in spirit they're the same.
Berlin was here also, no?
Berlin was here, but
I don't think they really saw eye to eye from what I know.
Zimmerman was here, Belrose was here.
Right, so the formula is somehow etched in the, I don't know if this lecture room was here, but the formula is etched in Fault Hall. I guess in the walls of Fault Hall you can still find scribbles with that formula. So that's the formula. Well, if we look at this formula, what happens is it's a standard, if you apply stationary phase, you will get this asymptotic expansion where you get powers of h, and each power of h comes with two derivatives. Well, the way it works here is you divide, you differentiate one of your symbols in xi and the other one in x, j times. So you get, in principle, better decay on h, but the price to pay is you have to differentiate more. Right? So yeah, and you can actually, an exercise for differential operators, this series terminates, and then that's actually an exact identity. So you can check it. It's not, it's not that mysterious to check. Now, if I go back to this picture, you can see that it seems that I might be in trouble. Because if I differentiate my symbol, so let me call it chi y, which is going to be like that. So this is a smoothened out version. If I differentiate it chi times, how big can the derivative be?
When you apply this, you will only need a certain number of derivatives.
That's right. So it's eventually you only need a finite number of terms.
Do you know how many? Because I think
It depends on the fractal uncertainty exponent. So if the fractal uncertainty exponent is like beta, then you will need about 1,000 over beta derivatives.
that's a bit of a nasty thing for variable curvature.
Well, yes, even though the underlying manifolds are still, but that's right. That's one of the things that one has to handle. But if you look at the derivatives of that, well, the jth derivative decays like h to the minus j, right? That's and so that's pretty bad. If I try to stick two pieces like that into this formula, then what I will see is I will lose h to the minus j here and potentially h to the minus j there. And then my asymptotic series, that makes no sense. Usually the rule is if the asymptotic series makes sense, as in each next term decays faster in h, then you can prove this formula. That's how it usually works. That's of course you still have to prove it in U, but it's a good guideline for when this formula can be true and when it cannot be true. However, what saves us here is that if we look at this picture, the derivatives are not bad equally in all directions. And so in fact, here's my definition. I will say that my function a of x psi h lies in, I'll call this as L0 comma rho, and I'll fix rho strictly less than 1 if I look at the derivatives like that, partial jx, partial ky, a is no more than some cjk, h to the minus rho, let's see, I always forget which one, here j. So I'm,
Where's L0?
L0 is just in the notation. So in lone stock hopefully I will have a tiny bit of time to explain why the notation is like that. But for now, let's just consider this anisotropic class, where if you differentiate in y, what am I saying, psi, then you don't lose anything. And if you differentiate in x, you can lose almost h inverse. Almost h inverse. And by the way, I can also take this class, SL1 rho, where you replace this by cjk h to the minus rho k. Now, if you look at the smoothened versions of these guys, well, imagine that instead of h neighborhoods, I took h to the row neighborhoods of my set, which is not so much worse. So we'll have to address that. But imagine that I fatten my sets just a tiny bit by a power of h, which is almost like power 1. Then, after all of this smoothing out, but this technicality is actually important because it tells you basically how much you can localize. And that's we'll have to take it to the extreme. So we'll have to localize as much as this allows us. So if you look at this localization operator, this is really a quantization of the symbol. If I stick my h to the row here, then this is more or less going to be an SL0 row, this localization, this symbol. It's not smooth, but if you smoothen it out, that's the derivative bounds that you'll see. And this one is going to be in SL1, row. So what you can see here is that if A and B are both in the same class, then this formula makes sense. Namely, the jth term is like all arch of h to the 1 minus rho times j. So the point here is that if you look at this, and there is a reason for that. Unfortunately, the reason is a bit more complicated than just symplectic structure. The choice of quantization does seem to matter for this problem. But for example, if you look at the standard quantization, you look at this product formula, we're coupling psi derivatives with x derivatives. The change of the quantization itself chosen is important. If you chose a different formula, at this scale, yes, if you chose a different quantization by tweaking the phase function, you might get a formula that's not going to converge. And so it's well, technical, not technical, but it is an important point. But here the standard quantization works for us.
That may become very important
in variable curvature, yes. So
are you saying that the while quantization does not work for us?
the while quantization works, but if you change your phase function, let's just say take that phase function, add absolute value x minus y squared to the phase function there, e to the I over h, and then just add absolute value x minus y squared. That gives you the same pseudo-differential operator if a was a nice symbol, but on that scale. So once your rho is bigger than 1/2, you are not going to get a nice formula like that. That's
You have here somehow asymmetry, right?
that's right. That's right.
That's only because if you could have defined the microlocal lift instead of putting sort of multiplied by a y.
Right. Well, the while quantization would still work actually because it will.
Sort of maybe switch the whole
Yeah.
of what
I guess what. Yeah. So what really matters here for these quantizations is that if you look at A and B, which both satisfy these derivative bounds, you can always write the corresponding formula as a product of a bad derivative, which loses h to the minus rho, and a good derivative, which doesn't lose anything. And so as long as your quantization had a phase which looks like that, it's basically linear, quadratic in this way, then you can always write it out like that. And it's as long as you have somehow, it's related to Lagrangians. But I'll get to that in a moment. But that's, in primitive terms, these bounds, they do make this formula work. So you can make sense of quantizing either symbols like this or symbols like that, and you can multiply them, and you will still get some sensible product. Now, however, what we're doing here is so let me erase this. So what we're doing here is we are multiplying two different quantizations, right? And so here's a theorem which follows from the one that I just erased. Theorem. So assume x and y. And so now you see the unfortunate side effect of this business is that I cannot take rho equals to 1. This barely doesn't converge. So I will take rho less than 1 in all of the arguments. So I'm going to assume that these are the sets. And I'm going to assume that now I'll fatten them out. So for example, I can assume delta is still strictly between 0 and 1, constant CR. And I'll assume that it's on scales h to the rho to 1. So I can make them a bit fatter. I can think of them as unions of h to the rho sized intervals. Then there exists beta, which depends on delta, and the regularity constant, which is bigger than the standard bound, such that, so how do I rewrite my thing here? I'll write it as a product of ax upage of AY, of two pseudo-differential operators. So this needs a proof, but once you know that this formula makes sense, and you have that previous theorem, that's not too hard to show, is going to be bounded by CH to the beta. And here you have to suffer a little bit of a loss, because you fatten things out. So if you take rho very close to 1, you first, you carry your argument through, and you get this fractal uncertainty exponent. No, it's true for each row. It's true for each row. It's just your loss at some point might be too big. You still want it to be positive, so you want to choose your row so that. Right. So fix. Right. Let's fix this. You're right. They should be. Yeah. You don't have to. Yeah. So you can quantify how much you lose, and you should choose row close to 1 so that this loss doesn't, that doesn't kill your gain. Where AX is an S. I keep forgetting. So this I'm afraid I'll just have to copy because I will otherwise. The notes for that, by the way, are on the website. AY is an SL1 row, so they're in two different classes. And then support AX is an Xi contained in X. And support AY is in X contained in Y, like that. So you can think of it as AY being, AX being like this. AX, if this is X and this is Xi. And AY, I'll draw it here, being like that. So you can convert this fractal uncertainty principle to this semiclassical statement, and you see that what you're doing here from a point of view of semiclassical analysis is ridiculous, because you're multiplying two symbols which live in these two completely, they live in two different classes. And if you look at, say, the commutator formula for these, or depending on the way you chose the product, you see that you might get a product of two bad derivatives when you do this asymptotic expansion. And so that's something that would be rather bad. And so the product of these operators, you cannot write it out really as a quantization of any symbol with any reasonable derivative bounds so that this microlocal algebra would work. However, you can estimate the L2 norm of the product. And in fact, these two things don't contradict each other. They actually make sense, because if this was a quantization of some nice symbol in a calculus with nice properties, the L2 norm of a quantized observable as h goes to 0 is like the sup norm of the symbol. And the sup norm of the product of these things is still 1. So it's somehow this statement, it goes completely perpendicular to the semiclassical or microlocal thinking. But that's an interpretation, and then as you can see, the proof of the statement is not going to involve basically any semiclassical analysis, and will be presented basically right now. Well, first, any questions?